Okay, apologies for the croaky voice. That's what whooping cough does to you. Welcome to the second subtopic of the atoms and nuclei topic, and that is the structure of the nucleus. So in this first video, we're going to really focus on the structure of the nucleus, and then the second video we'll look at some of the conservation laws and how they apply within the nucleus. The applications of this topic really overlap with all the other topics. So we've already looked at the cyclotron and firing charged nuclei into an existing nucleus in a cyclotron to make a new nucleus, normally a radioactive one that we might use for something like PET scanning. So it undergoes beta plus decay, so that sets up electron-positron annihilation, which we've already looked at. This stuff is also very important to understand alpha, beta and gamma decay, which we're going to cover in the next subtopic. And in what will actually be our final subtopic for the year, which will come after alpha, beta and gamma decay, we're going to look at nuclear fission and fusion. And what we're going to learn about today is going to be related to why we get so much energy out of nuclear reactions, and also in conjunction with how we can make new isotopes in a nuclear reactor. So I think that'll become apparent as we look at those two topics. Cheers. Okay, this first part should be very much revision from your even back as early as probably year 9. Hopefully we all know by this point that an atom consists of protons, neutrons and electrons, and we find the protons and neutrons in the nucleus. And protons and neutrons have an approximately similar mass, and the electrons are much smaller in comparison to the protons and the neutrons. The proton has a positive charge that's equal and opposite to that of an electron, and the neutron has no charge. And this word may be new to you. We're going to talk about the word nucleon. So a nucleon refers to something that's found in the nucleus. So that can either be a proton or a neutron. So this is the sort of standard notation we use to identify a nucleus. So we use, firstly, probably this number down here is most important. This is the atomic number, the Z number, and that tells us the number of protons within a nucleus. So in this case, if we've got 6 protons, that nucleus must be carbon, because that's what carbon is. Carbon is an atom with 6 protons. We then have this number up here. Somewhat confusingly, it's called the mass number and given the symbol A, even though an atomic number is given the symbol Z. Yep, go figure, but I didn't make up the convention. This is just how we do it. And this number up here, the mass number, tells us, well, we can think of this two ways. It tells us the number of nucleons that are in that nucleus. So that basically is the number of protons plus the neutrons. So in this case, we've got carbon, what we call carbon 13, so carbon with a mass number of 13. So it's got 6 protons. It has to have 6 protons because it's carbon. Therefore, it must have 7 neutrons. 6 plus 7 equals 13. So, hopefully that's very much just recapping what you've learnt in year 9, 10 and 11. Okay, into some more interesting stuff. Up until this point, we have really only learnt about, well, 2 forces. We've learnt about gravity, which is a very weak force that pulls all masses together. And then we have learnt about the electrostatic force, which tells us like charges should repel. And if we think about the nucleus of an atom, we have these positively charged protons all grouped together. And the laws of electrostatics said those should try and push each other apart. So if we think of this case here, a proton here and a proton here, electrostatic force between them is trying to push them away. So, based on what we've learnt today, there shouldn't be any atoms with more than 1 proton. The universe should be made of hydrogen, because the electrostatic force should push all those protons within the nucleus apart. So this is where we're going to introduce another fundamental force. So we've learnt about gravity, we've learnt about the electrostatic force, and now we're going to learn about the nuclear force. In this case, the strong nuclear force. There's actually two nuclear forces, a strong and a weak nuclear force. Don't need to go into that this year. We'll come into the course next year a little bit more with the standard model. However, what is this nuclear force? At short distances between nucleons, nucleons exert strong attractive forces on each other. These forces become negligible at separations of more than a few nucleon diameters and become repulsive at extremely short distances. So what does this all mean? Let's look at this graph. This red line here shows the electrostatic force. It's always repulsive, and as these two nuclei get closer and closer together, it basically becomes more and more repulsive. They're pushing apart harder and harder. However, the strong nuclear force at very, very, very short distances, like the electrostatic force, is repulsive. Then, and the distances we're talking about here are a few nucleon diameters. So you think about the diameter of a few nucleons across. It then becomes attractive for this small zone in here of a few nucleons distance. Then it quickly becomes basically negligible. So it becomes so small that it basically is insignificant. So we have these two forces at play within the nucleus, the strong nuclear force and the electrostatic force. And it's the sum, if you like, the vector addition of those two forces that tells us whether a nucleus that holds a nucleus together. So initially it's repulsive, so that the two protons can't get too close to each other. So they can't basically squash into each other. Then we have this short, small range here where the strong nuclear force is greater than the electrostatic force. Compare that distance there to that distance there. And in this region, the two protons will be attracted to each other. And this strong nuclear force exists not just for protons but also for neutrons. But neutrons don't have this electrostatic repulsion force. Then, quickly the electrostatic force becomes much larger than the strong nuclear force, so they go back to repelling each other. And we'll learn in the next topic, this is why we don't have really, really, really big atoms. This is why the largest atom you can have has an atomic number, the largest stable atom you can have has an atomic number of about 83. Because if you have more than 83 protons, the ones at each side are so far apart that the strong nuclear force can't hold them together, so that they basically disintegrate, decay, become unstable. That's what the next topic is all about, so I won't say too much now. So, let's use a little fairy tale analogy here. Out in this region here, the electrostatic force, the red, is much greater in magnitude than the nuclear force. So overwhelmingly, the green line here is repulsion. So we're going to call this the Shrek zone, the far, far away zone. If these two things are too far away, the red indicates the electrostatic force, the blue, the nuclear force, the green, the total, same as in the diagram below. So you can see the net force here is repulsion. These things will push away. In this region here, we're going to call that the Goldilocks zone. Remember, the porridge, the temperature of the porridge, not too hot, not too cold, just right. So in this region here, the strong nuclear force is attracting there, and that is greater than the electrostatic repulsion. So the net force is an attractive force. So this is that zone where the nucleus with more than one proton in it can hold together. If we get into this zone here, which is basically less than the diameter of a proton or a neutron, so in a sense you're trying to squash the two together, you can think of it. Bit of a simplification there, but I think that works. Both the electrostatic force here is repulsive. Sorry, the strong nuclear force here is repulsive. The electrostatic force here is repulsive. So the total force in this area here is repulsive. So you can't get the protons too close to each other as well. So that hopefully explains what holds a nucleus together. Okay, let's talk about isotopes. So isotopes of an element have the same number of protons and therefore electrons, but have a different number of neutrons. So we have here two isotopes of carbon, carbon-12, carbon-13. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. So that's all we mean by isotopes. Hopefully that should be revision. Now, do you know how sometimes people say it's what's on the inside that counts, it's not what you look like on the outside? Well, sorry, but with atoms, at least in this context, it's what's on the outside that matters. So when atoms interact with each other, so form chemical bonds, we're almost going into the chemistry here, it's the electrons on the outside that interact and that are exchanged. So isotopes, because they have the same number of protons in the middle and the same number of electrons on the outside, look very much the same on the outside, so they will interact with other atoms in the same way. So carbon-12 and carbon-13 will react chemically identically because the difference of one neutron in here has very, 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 in fact, no significance on what's happening on the outside here where the electrons are. So they basically look the same on the outside, therefore react the same chemically.